Okay, so this is 9.3, inscribed angles. Calendar's a little bit off. We've already covered a little bit of 9.3, but we're going to spend some time finishing 9.3 on Monday, and then we'll start 9.4 on Tuesday. That's the important part. Okay, inscribed angles. We learned this last time. We have the central angle, uses the center of a circle, and then the arc that it covers is called the intercepted arc. Now, if I move the angle from the center to another point on the circle, some very interesting things happen. We call this an inscribed angle, mainly because the angle is inscribed by the circle. We were talking about circumscribed versus inscribed. This is an inscribed angle, and it covers the same arc. Notice how the intercepted arc is the same size. Didn't change at all. So it's still called the intercepted arc. Now, instead of being a central angle, though, it's an inscribed angle. Okay, let me see if I can get to my desktop here. I'll open up a GeoGebra file here. We talked about this in class a little bit, but I want you to be able to see it. If I draw a circle here, and then I put some points, some segments on here, let's see if I can draw an angle. Nope, I want it to be on the circle. Okay. So if here's my angle, I can measure the angle here. Okay, so it's 24.54 degrees. Now I think it's obvious that if I take E and I move it around, the angle's going to get bigger. We can see that, right? Somewhere around here, it's a diameter, right? Because it's 90 degrees. If we keep moving around, the angle changes size. But what I want to know is if I grab D right here and I move it around, what's going to change? Think about what you think will change. If I take D and I drag it over here to the right, will the number change? Will it get bigger? Will it get smaller? Most people feel like it should get bigger and then start to get smaller again. And this might surprise you, but if I take D and I drag it around, it doesn't move at all. And the reason for that is it's covering the same arc, CE. So the measure of arc CE is still going to be the same amount. It doesn't change. And therefore the angle covering that arc can't change either. So no matter where I put it, that arc number doesn't change. Okay? So when we look at the value of the intercepted arcs, let's talk here. We don't know which angle's bigger. Well, I think I can look at this and say, hey, look at that. The red angle is bigger. The question is, how much bigger? Okay. If I go back to my GeoGebra file here, and I were to draw a central angle between CA and AE. Okay, so now I have my central angle compared to my intercepted angle. If I want to measure this, I want to think, what do you think it's going to be? At 90 degrees more, half as big, twice as big, ends up being twice as big. So 31.45, if I double that, I end up with 62.9, give or take. Okay. Now if I adjust this to be bigger, let's make it a little bit easier number, 150, give or take. This one's going to be 75, that's half as much. So the intercepted angle is half as much as the central angle. So when we say how much, it's twice as big, and we can see it pictorially here. We see central angle here, same size as the arc. Well, over here, if the arc is A, then the inscribed angle is half as big. So when we go from arc to angle, we cut it in half. But what if I know the inscribed angle value? How big is the arc? Well, twice as big. So when we go from angle to arc, we double. When we go from arc to angle, we cut in half. And that's kind of the pattern that we have to see. The arc is twice as big as the angle, or the angle is half as big as the arc. Okay, so we know the measure of the intercepted arc, then you cut it in half. If you know the angle, then you double it. So in the circle below, draw an inscribed angle. Okay. If we say this is angle B, then we know the arc is 2B. And if we draw an inscribed angle here, we mark it as the arc is A, then we know the angle is going to be half. All right, so now you have time to work on 16 through 21. Pause the video if you need to. All right, now let's use the information we just found to find the values of the missing variables. If we just isolate and look at just x right here, x is 80. The arc is 80. That means that x is half as big. Therefore, it's going to be 40. And if we look over here at y, we notice that the angle is 55. But how big is the arc? We have to double it. So we take 55 times 2, and we get 110. Now the last one was, hey, this is a diameter, right? And if that's a diameter, then this part over here is a semicircle. Should be 180 degrees. And if I want to get rid of, if I just want these, then I got to take away the 110. I'm left with 70. So z equals 70. Okay, that should help you with problems 1 through 21. It's the same kind of process. If you got that in your notes, you may have had to pause at various times throughout the example to fill it in. But hopefully you got it filled in. Rewind, play it again if you have to. But now you should be able to do problems 1 through 21. All right, now, if two inscribed angles of a circle intercept the same arc, then the angles are congruent. We learned that from the GeoGebra, right? No matter where I move this, it's going to be the same value. Okay. Now, if angle 1 and angle 2 cover the arc AB, and arc AB equals 120, let's just look at angle 1 first. If we just focus on angle 1, here's the angle, there's the arc. Well, we've got to cut it in half. If I cut it in half, I get 60. And since angle 2 covers the same arc, we know that it's also 60. Okay, now you can do 22 through 24. It might take some practice. It might take some work. But I think you can manage it if you weren't there in class. We talked about it in class a lot. Now, this rule here blows people's minds a little bit, and I want to talk about it for a second. If I make this exactly 180 degrees, it's going to take too long. Let's do this. Delete it. Delete it. And then if I were to make this into a line going through here to here, okay, I find the intersection of this point here. Now CB is a diameter, and I take some segments and I create an angle right here. Now CB is a diameter. The angle measure of BDC right there is going to be 90 degrees exactly. Now what blows people's minds is it covers that arc, right? Arc CB. That arc never changes, so no matter where I drag this, it's going to be 90 degrees. It's going to be 90 degrees no matter where I put it. And seeing that visually in front of my face, just I don't know, something that does something to me. Now over here, it's going to be the same value. It says 270 because it's measuring the wrong arc, or the wrong angle. But no matter where I put it, it's going to be 90 degrees. And that plays into account right here. Angle B is a right angle if and only if AC is a diameter. If and only if means it's a biconditional statement. So if B is a right angle, AC is a diameter. If AC is a diameter, then B measures 90 degrees. And measuring 90 degrees on a circle is very important. We use it a lot because we already know a lot of information about right triangles, right? We have special right triangles, 30, 60, 90s, 45, 45, 90s. We can do some Pythagorean theorems. We have Pythagorean triples. So if you can find a 90-degree angle on a circle, you're sitting pretty. Like in this example, if CE is a diameter, then arc CDE is a semicircle. And that means that the measure of angle 3 is 90 degrees. Example 9.91 or 9.19. Okay, so now if we look into more of an inscribed polygon. Okay, if I want to draw, let's switch over to GeoGebra. Let's change this triangle into a quadrilateral. We're going to turn it into a polygon. Let's not make it regular. Let's make it just a regular polygon, non-conventional polygon. There we go. Now, if I turn it and I draw it here at C, and I create a new point. Here we go. C, D, E, B. Come back to C. Here's my polygon. All right, now I drag these. That's not going to work. It's going to be ugly. All right, I drag them. here's my polygon. It doesn't matter what shape the polygon creates. There's some pretty interesting things that happen when we talk about the angles. So let's go ahead and bring up the angles of the polygon. There you go, 134, 110. Is there anything special about those two values? Looks like it adds up to 240 something. Nothing really all that special, but now let's see if we can find some more special values here. What happens is this value never changes until I move this value here. That's fine. I think we can understand that part. Now, if I make this one close to 60 as I can, it's pretty close. 60 plus 120 makes 180. Coincidence? Let's move it a little more. And look at these ones. This one's pretty close to 45, right? 45 plus 135 makes 180. Coincidence? I think not. The opposite angles of an inscribed quadrilateral have to measure 180. The opposite ones. So right here, angle C and angle E, they have to measure 180. Have to. There's no ifs, ands, or buts. I could change my quadrilateral. Go ahead and undo this, and I'll make a different quadrilateral, and the angles will still be the same. I can make it any quadrilateral I want right here. And as soon as I bring up the opposite angles, you'll see that they add to 180. 95 plus 85 adds up to 180. What's really cool about that is these values, if I move this one, it doesn't change. If I move this one, it doesn't change. They're still covering the same arcs. But if I move E around, 138 plus 142, or 42, sorry, makes 180. So right here, the opposite angles have to be supplementary if it's inscribed in a circle. So if measure 475, how big is angle 5? They have to add to 180. So we take 180 minus 75, and we get 105. And that's how big angle 5 is. You're going to use this one a lot. Okay, especially on 25 through 30. Let's go ahead and take a look at those, just so we can get an idea of what we're talking about for 9.3. Okay, 25 through 30. All right, so I'll zoom in a little bit. So if angle arc BCD is 136. Let's pull out my pencil here so I can write a little bit. This whole arc over here is 136. That means that the other arc on this side up here is going to be 360 minus 136. Borrow here. Gives me 4, 2, 2, 224. Now, since they are congruent to each other, see here, it says just those two angles are congruent to each other, I have to share this 124 between these two different angles. So I divide it by 2 to get 112, and I say that angle Z is 112. Not too bad so far. Okay, pull out my eraser so I can have some more room to work. Huh, never seen that before. I'm not really used to having to use this eraser on the PDF. Works pretty good though. Okay, so we know what Z is. Now, since AC is obviously a diameter, we know that angle Y should be 90 degrees because it's angled of a diameter, and angle X has to add to 180 with Y because they're opposite angles of a quadrilateral. So we know it also has to equal 90. And we're done. Over here, if this one's 100, X has to be 80 because they have to add to be 180. If this one's 102 and this one's Y, then this has got to be 78 because it has to add to be 180. The measure of BCD, this arc is angle Z. How big is this arc going to be? If X is 80 and it's an inscribed angle, then the arc BCD has to be twice as big as that, so it's got to be 160, so Z should be 160. See how these things all kind of play together in the same kind of concepts? Oh, it's not going to let me do it. So there's some kind of homework prompt, so you can work on your homework. All right, so if all the vertices of a polygon lie on a circle, the polygon is inscribed. We talked about inscribed versus circumscribed a couple times now, but you need to understand the definition of inscribed and circumscribed. Okay, circle is circumscribed on the outside. The polygon is inscribed because it's on the inside. Hopefully that makes sense. Let's talk about homework problem 31, the definition of a square. It says on question number 31, okay, draw each polygon inscribed in the circle if possible. Can the quadrilateral always be inscribed? So if I draw a square on here, can a square always be inscribed in a circle? Well, we talked about the definition of a quadrilateral having to have its opposite angles add to 180. I hope we remember that. I don't know how to get rid of that thing. I don't want that. Okay. I wanted to draw a 90-degree angle right here. We know that a square has 4 90-degree angles. So does that mean that the opposite angles are always 180 degrees? They always add up to 180. So that means it can't always add up to 180. It doesn't. Now the question is always. Can a quadrilateral always be circumscribed or inscribed? And the answer is yes. A square can always have a circle drawn around it. It's perfect. We go on to rectangle. You draw the rectangle on there, and you kind of think about what does it mean to be a rectangle, and you move on. You draw a kite. Can it always be? Yes or no. Explain why it can't be or when it can't be, and you go through those. So that's the homework help. The rest of the lesson is pretty much just working on those problems and thinking about what it means to be a rectangle, and what it means to be able to be inscribed. Hopefully these pictures are helpful. You might want to pause and look at these pictures to help you. Any questions? Yeah, so a kite, sometimes it can be, and sometimes it can't be, depends on certain circumstances. All right, a rhombus, looking at the picture there, I think you can make your own conclusions. A definition of an isosceles trapezoid, this one you might want to think about a little bit. This is a great question. Draw it a couple times. Think about the opposite angles in an isosceles trapezoid. Okay. As far as the calendar goes, this is what I want you to notice. Thanksgiving holiday is coming up really fast. My hope is that we will be able to get through. Now we're not doing 9/5 or 9/8. Okay. So we've got extra days to spread out the information. So we're doing 9/3, 9/4, and stuff like that. But the hard date right here is this test. We are taking the test on this Monday. And then we're going to do a couple Chapter 6 stuff. Thanksgiving holiday. Come back, do 6.2, and then we're going to take the test on the Chapter 9 retest, which is super important because Chapter 9 test is pretty difficult. And that's kind of the calendar for the upcoming little bit. Summarize what you learned. And I'm done. Make sure you summarize what you learned. That's important.